Okay, welcome back to week one. This is part 4 of our discussion of Python basic capabilities. I have increased the font size for my shell and also increased the font size for my program editor. Hopefully that will make things easier for you to read, although I will be overlapping the presentation of the slides. In part 3, we took a look at the low-level data types. For example, 5 is an int, 2.7 is a float, hello in quotes, or hello in double quotes, or hello in triple single quotes, or hello in triple double quotes. Those are all examples of str or string literals, values. And we also have Boolean values, true with a capital T, false with a capital F. And occasionally we're going to see the special value none pop up, which is a value that a variable can refer to indicate no specific value. Now, notice here that none is a value that the shell does not display any representation of by default. This is a case where we can use our print function that we talked about to display a human user readable version of none, and it's just, of course, the same characters, N-O-N-E with capital N at the beginning. We took a look at concatenation using plus of strings. Okay, I couldn't think of an example there for a minute. But here we have hi, and then I'm concatenating GH to get hi, H-I-G-H as my result. The shell simply executes statements and displays the source code representation of those statements, whereas in a program, we can write a sequence of statements that we can store and execute all at once. So here I've got this prog1.py program file, and if I say run module, that gets executed back in my shell. We saw that print will take multiple arguments, and by default display those arguments with a space in between each one, but you can use this keyword argument separator, sep, to specify a different argument separator in the output. So here we have these commas displayed between hello and Bob and 3.666 blah blah and true. Okay, and then finally we had the len function that we used to, whoops, accidentally pulled up my calculator. I don't know what magic key sequence I hit to do that. Anyway, all right, so len of hello is 5. Onward ho. So now we're going to introduce a collection type. This is actually a sequence type, meaning that the values are stored in sequence from the sub-0 item, followed by the sub-1 item, sub-2 item, and so on. And this first collection type we're going to investigate is the list. It's fine to keep track of values individually. Here we have FAHR set to 80, and we computed cells using this computation inside of our program, and then we could display this useful output text to a user running our program that 80 Fahrenheit is 26.66666, etc. Celsius. Okay? But rather than keeping track of just individual values, we occasionally, in fact, we frequently, need to keep track of a whole collection of values. And a list might contain, for example, all of the weights of patients in a doctor's office, all of the scores for an exam for a class, all of the stock market prices for every trading day during the year 2019 for, let's say, Apple Computer. We can imagine lots of lists of values, and in Python we represent those by putting a sequence of values in square bracket characters. So if I say, as is shown here on this example slide, let me scoot my shell over a little bit. Okay, so I'm creating m as a variable, and I'm assigning m to refer to this list of 4 int values. 7230, and I use square brackets around the sequence, around the list, and I use commas to separate the items in the list. When I now ask to see the representation of m, what the shell shows me is that list in square brackets, and if I ask for the type of the thing that m is referring to, I get told, okay, that thing is a list. Now, I can index the individual items within the list by using subscripts from 0 up to 1 less than the length. By the way, I can ask for the length of a list just as I can ask for the length of a string. Okay? And m sub 0 is how I access how I access the initial item, the sub-zeroth item of the list. So that's 7. M sub 1 is 2. M sub 2 is the item value 3. And m sub 3 is actually the last item in this list, which has a value of 0. Now, it turns out I can also use reverse indices. I can start from the end of the list and access that item as item sub -1, and I can count all the way back to -n, where n is the length of this list. So m sub -1, well, let's just display m again to remind ourselves. There's m. M sub -1 is the 0. M sub -2 is the 3. M sub -4 is the initial item with value 7. If I go outside the bounds of the list, I get an error. Okay, so m has these 4 items within it, items with values 7, 2, 3, and 0. M sub 4, it's easy to do this by mistake because you think to yourself, well, there's 4 items in this list. I want the last item, m sub 4, and I get yelled at. All right? The list index 4 is out of range because the last item in the list using positive indexes is sub 3. All right, so m sub 3 is the final item in the list m. M sub 4 is beyond the end of the thing. M sub -4 is correct. Whoops. Well, let me display m again before it goes off the top of our screen. M sub -4 is correct. That's the first item. M sub -5 would be beyond the range. It would be in front of the beginning, and that is going to be an error. Okay. We can modify items in a list by assigning different values to those items. Technically speaking, in Python terminology, we say that a list is mutable. A collection is mutable if you're allowed to change items within the collection. So here I have my list M, and if I say M sub 2 gets a 5, all right, well, let's think about this. So what is M sub 2? M sub 2 is this item here whose initial value was 3. When I say M sub 2 gets a 5, that actually modifies that sub 2 item within the list M. And the other 3 items remain unchanged by that. I can use addition to do concatenation, just as I can do with addition of strings. If I add one stir to another, that concatenates the stirs. Similarly, if I add one list to another list, that concatenates the lists. So M is the list currently containing 7250. And if I add the list 471, I get a list of 7 items, 7250, 471. Now that addition did not modify M. What that addition did was to take the current value of M, which is a list of 4 items, concatenate a list of 3 items to create a list of 7 items, and then display to me that list of 7 items. But M itself is not actually affected. If I had wanted to modify M, I could have used our assignment operator plus gets and some list. Let's use 471 here. So remember that plus gets, so M plus gets this list means M gets M plus 471. All right, so in this case, we get the value that M is currently referring to, which is the list 7250. We're going to append 471 to that list, resulting in a list of 7 items, and then we're going to change M to refer to that list of 7 items instead of to its original list of 4 items. Now M refers to those 7 items. Repetition also works for lists. If I were to say M times 2, that would give me a list that repeats M twice. Now M itself is not being changed here. If I wanted to, let's say, create a list of, let's say, timings for marathon runners, and let's say I have 1,000 marathon runners in my race, I could say times gets 0 times 1,000, because initially I want to create this table, but I don't have final times yet, so I'm just going to fill in all these times with zeros, and that's okay. I've got now this times list containing 1,000 values of 0. And when I display times, it goes zooming off the top of my screen, okay? But it does contain 1,000 values, and each of the values in there is a 0. In addition to the plus for concatenation and the times for repetition, the list collection type has a number of named operations that we can perform on a list object. And the proper terminology for these in Python is methods. A list is an example of a built-in so-called class, and methods on a class are the functions that you can invoke to interact with objects of that particular class. So I can do an append to a list. Here I've got my list M. If I were to say m.append let's say a 6. What that does is adds this argument value 6 to the end of the list. It actually does modify m, so that m now is the same as it was, but it has a 6 added to the end. m.insert allows me to put a value anywhere I wish. Append always goes at the end, but with insert, I specify the index ahead of which I would like to insert some value. So let me say insert ahead of position sub 0, let's say another 6. So position sub 0 currently contains a 7, but in front of that 7, I'm going to insert another 6. All right, so now I still have the 6 that I appended, and now I have a 6 that I inserted at the beginning. If I say m.insert 4, let's say 6, all right, now you might get confused about that and think, oh, we're inserting the 6 ahead of the 4. No, we're inserting the 6 ahead of position sub 4. So this 6 is at position sub 0. 1, 2, 3, 4. This 0 is currently at position sub 4, and I'm inserting the 6 ahead of that 0. All right, so here's the 6 that I just inserted, and it now occupies position sub 4. I can remove a particular value from a list by saying m.remove, and then just give the value. Let me say remove 0, let's say. So in this case, 0 is not an index. 0 is a value for the remove method, and the remove method scans through the list, discovers the first 0 that exists, and removes that from the list. All right, so now I go from this, I got a 6 immediately followed by a 4. The 0 that used to be in between those has been removed. If I say pop, that will return an item from the list that's located at a certain index, or at the end of the list, that is the length of the list minus 1, if I didn't provide an index. All right, so the case here is I've said m.pop, and I have not specified an index. That means that the item returned is going to be the item at length minus 1, which is always the index of the last item in the list. And that item will not only be returned by this pop method, but it will also be removed from the list. So when I say m.pop, that will return this 6, but also remove that 6 from the list, so that if I look at the list now, I see that the 6 is no longer there. If I say m.pop again, well, the item at the end of the list following the first pop is the value 1. So that value 1 is what's popped. And now if I do pop again, that gets me the 7 from the end of the list. I can use an index if I wish. So I can say m.pop 1 to remove item sub 1, which is this other 7. All right, so now I've done 4 pops, and what had been a list of 9 items is now reduced to a list of 5 items. Counting will count the number of times that a particular value occurs and return that value. So m.count of 6 in my appended and inserted and popped list here gives me back that there are 2 6s in m. m.count of 5, well, 5 would just be 1. m.count of 7, well, I removed all the 7s. I popped all the 7s, so I've got no 7s remaining. And I can sort the list. By default, this will be in ascending order. Technically non-descending order, since we might have some duplicates. In fact, we do have a couple of duplicates. We do have 6 appearing twice. So when we sort this in non-descending order, the result is going to be 2, 4, 5, 6, 6. If I now do things like m.append a 3, m.append another 3, m.insert, let's say a 5. Hello. Oh, I made a mistake. I forgot to specify both an index and a value to be inserted. So I need to say m.insert. I meant to insert this at position sub 0. So now I'm inserting my 5 at position sub 0. All right, I've modified my list M now with 2 appends and an insert. And if I sort, now I've got 2, 3, 3, 4, 5, 5, 6, 6. I can also reverse whatever is currently in the list with the reverse method. And that does what it sounds like it should do. So these are 7 named methods that I can use to find out about and modify the list. There are several others that we just won't get into. And here we have examples on slide 7 that are similar to the examples that I showed you interactively. And you can step your way through and see what these examples are about. In fact, you could pause the video and try these examples if you would like. Okay, it occurred to me I wanted to make one remark about why I chose this variable name m to contain my list. If you create a string, it's easy to just use s. S gets hello. If you use, for an integer, you might say I gets 12. For a floating point number, you might say f gets 12.7. or x gets 12.7. So you might think, all right, well, I'm creating a list. I'm just going to call it L gets 3, 4, 5. And that works. But notice how similar in this shell the L looks to a 1. Especially if the font size is small, it's difficult to tell the difference between a lowercase l and a 1. So I urge you never to use lowercase l as part of, or at least as the first character in a variable name, or even the last character in a variable name. It's too easy for somebody to misread and think that you're typing a 1. I use M just because M comes after L, and I, I think to myself, well, I don't want to use L, so I'll use M. All right, so that's that. By the way, just to illustrate the worst possible thing that can happen here, the Arial font, once upon a time, was a default font, very widely used in PowerPoint presentations. And if you were trying to write a technical presentation in this Arial font, it was quite catastrophic because the 1 and the lowercase l and the capital I in the Arial font are all 3 just vertical lines with no cap or no base. And consequently, if you were trying to write code examples using Arial, you couldn't tell whether what you were looking at was a 1 or an L, lowercase l, or capital I. It was pretty horrible. So in this font, you can use capital I, and it obviously is a capital I, but I still encourage you not to use little l as a variable name, to avoid getting confused that it might be a 1. So, next up we have the exciting topic of logical versus physical lines in Python. These things that I've been doing here, m.sort, m.reverse, actually just plain m by itself, s gets hello, I gets 12. These are all examples of what are called statements. They cause something to happen. They cause a computation to be performed. They cause a function to be called. They cause an object, like the list m, to be used, and so on. And in Python, a statement has to exist on a single logical line. When we get to talking about loops and functions later, we'll discover that we can have what are called compound statements, which are a sequence of individual statements in which each individual statement occupies a logical line. Now, a physical line, to differentiate from a logical line, is any line that you type that ends with a new line character, that is, that ends when you press the enter key. And for the short statements that we've been typing so far, a logical line and a physical line have been one and the same thing. So if I say x gets 12, this is both a physical and a logical line containing a statement. And the statement says, change the variable x to refer to this integer value 12. What I can't do in Python, which may or may not confuse you depending on what other languages you're accustomed to, is I can't say x gets and then press the enter key and type the value of x on the next line down. Python yells at me that I have created a syntax error when I do this, because I cannot separate a logical line into two separate physical lines by just hitting the enter key. So this is very annoying, and the workaround that Python offers is, okay, well, if you insist on typing a logical line across more than one physical line, you can do that by pressing the backslash before you hit the enter key. So this is the backslash character. Now I hit the enter key, and Python says, oh, okay, I get it. You're trying to continue this logical line. Now I can type the 12 and hit enter, and Python is happy. So this backslash followed by enter allows Python, or causes Python, to pretend that you didn't press the enter key after all, and that what you actually typed was just x gets 12. By the way, notice that I keep pronouncing this single equal sign as gets. I do that because we also later will have a double equal sign, which is the is equal to operator. And I want to be careful to differentiate the assignment, the single equal sign, from the double equal is equal to operator. So I call the single equal sign gets, and later I will call the double equal sign the is equal to operator. Okay, so x gets 12. Works fine. And now if I ask to see the representation of x, I get told that it's 12. I can go completely bananas with these backslashes. I can say x backslash enter gets backslash enter backslash enter 1 backslash enter 2. And that did not work. Oh, I see. Okay, my mistake. I believed that the backslash enter was being ignored. That is the case in the C programming language, but apparently not in the Python language. Oops, I didn't mean to Now I'm compounding my error. I pressed S. I meant to look at X. All right, so X still contains the 12 that it did previously. But I can say X \enter gets \enter 12 enter, and that works fine. Although I'm not sure what I proved since I just assigned X the value it already contained. Let's do something slightly more clever. 123. All right, so that's how you can continue a physical line, or pardon me, how you can continue a logical line across multiple physical lines. Another way that you can continue a logical line across multiple physical lines is to use parentheses or else square brackets or curly braces to extend the statement. All right, so if I say X gets open parenthesis, now Python is happy to let me type as many enters as I want until eventually I type a closing parenthesis, and parentheses around the integer value 1234 is just the integer value 1234. Okay, so rather than using the nasty, ugly backslash, I can use a pair of parentheses. And this allows me to do complex arithmetic expressions, 34 minus 52 plus, and then on the next line down, I can say 2 cubed minus, and the next line down, 14 floor divided by 3. Okay, and so if you do need to have some long arithmetic expression, you can just enclose the thing in parentheses, and that works totally fine. Likewise, if I am defining a list that contains a large number of values, here I'm just using n as opposed to m for my list name. I can say n gets, let's say 12, 13, 14, 15. Maybe I want a list of 12 values. I'll just hit the enter key. I want my comma, and then I'll hit the enter key and keep going. 16, 17, 8, 9, 1, 2, 3, 4. I've got my list of 12 items, and there it is. Now, those enter keys that I hit are not preserved inside of the list in some way. I can just use the enter key to make it more convenient for myself to type in the values in that list. And certainly that's going to look nicer in a program file. If I say n gets, let's say 1, 2, 3, 4, 12, 14, 16, 18, I can change this. I can make the columns look nice. 22, 25, 27, 29. Okay, and so now I have a tidy looking list in my program. And let me print n and run it with F5. All right, so there's my list. All right. As I showed you, you can use len to get the length of a list, just as you can use len to get the length of a string. If you want to step through and do something with each of the items in a collection, such as a list, the most common way of doing that is to use something called a for loop. And the for loop causes a variable whose name you make up to step through each of the items in some so-called iterable. Now, an iterable is something that you can step through the items of. So it sort of defines itself in a way. A list is a sequence of items. And what we're doing in this for loop, let me type in an example of a for loop. Let's use, silly me. Okay, so when I executed prog1 by typing in this list n and then saving it and hitting F5, that restarts the shell, executes the program in prog1, and restarting the shell is going to cause all of these previous variables that I had created to be forgotten. So m no longer exists. But fortunately for me, I do have n that I created within the program. And so let me show you an illustration of a for loop. I can say for value, well, not val in n. Now, n is a list. N is a collection, or specifically a sequence, of item values. And this variable val, whose name I just picked out of thin air, is going to be set to each one of these values in this list, one value at a time. So the first time through the list, val is going to be set to 1. I must have a colon to conclude this introductory part of my for loop. And then within the body of the for loop, I can have as many statements as I wish, indicating what I would like to do with the current variable val. And I'm going to do something really simple. I'm just going to say print val. Now, it's possible in the body of a for loop to have many statements, but I'm going to only have one statement, just this print function call. Notice that print is indented here, and in fact that is absolutely required. If I did not have print indented in from where for starts, Python would yell at me that I have a syntax error, like it's yelled at me various other times for having syntax errors. Now, to persuade Python that I'm done typing this for loop, I need to press the Enter key a second time, and Python will realize, evidently this programmer is done typing in this for loop description. So let me run it, and there we are. Let me grow this window just a little bit so we can see everything. So n is this list containing 12 items. In the for loop, I'm iterating through or stepping through all of the items in n. And this variable val is going to be set to each one of those item values one at a time. So val initially is set to 1, and we print the value of val, which is 1. Print, by the way, remember by default displays things on a line. So 1 is displayed, and then we get an enter key or a new line character generated automatically. When the first print is done, then val gets set to 2, and we print 2. Then val gets set to 3, and we print 3. Val gets set to 4, and we print 4. The fifth time through, val gets set to 12, and we print 12. Then 14, and we print 14. In other words, since there are 4, 8, 12 items within this list, that means we're going to run through this body of this for loop 12 times, printing out each of those values from the list. 1, 2, 3, 4, 12, 14, 16, 18, 22, 25, 27, 29, and then we're done. At that point, there are no items left in n, and so the for loop is finished, and I simply get back to a shell prompt at that point. Okay, so in this syntax description, in this structure of this for loop, let me re-highlight things as I go. For is what's called a keyword. It's a required word. In is likewise a keyword or a required word. And the colon at the end of this first line is also required. If you forget the colon, which is very common when you're beginning as a programmer, it's easy to forget that, and you'll probably get yelled at. Well, you'll certainly get yelled at, and then we just hope you can understand why you got yelled at because you forgot that colon. Now, var here is a variable name that you just make up. I chose the name val, but you could say x or banana or zebra or wxyz or whatever you want your variable to be. Then you have some iterable, which in our case is a list, the list referred to by the variable n. And then we have one or more statements that have to be indented within the so-called body of the loop. Now, the iterable could be a string instead of a list. Let's take a look at an example of a string. All right. Here we have an example in which we're using a string. Actually, let me show this example using a literal list rather than using the variable n. If I say for I in this literal list, 1, 5, 9, -4, 12. Okay, so here in square brackets, I've manually typed in a list of values for I to be set to one value at a time. And this time, instead of printing just plain I, I'm going to print I squared. All right, so I'm going to print 1 squared, 5 squared, 9 squared, -14 squared. Each of those is going to come out on a separate line because print automatically adds a new line at the end. There we go, 125, 81, 16, 144. I can be more elaborate in my body of code. I can say for I in, well, let me copy and paste this so I don't have to retype stuff. Okay. Print I, comma, squared is, comma, I squared. Okay? So now I have a somewhat more elaborate bit of output for each item in that list of 5 items. 1 squared is 1, 5 squared is 25, -4 squared is 16, etc. Hello is a sequence of characters in the same way that the lists we've shown so far have been sequences of int values. And so if I say for s in hello, what's going to happen here is that the variable s is going to be set one by one to the one character substrings of hello. Okay, so first s is going to be set to a one character substring containing h, then containing, then containing e, then containing this first l, then containing the second l, and finally containing o. So we're going to go through this loop 5 times, and I'm simply printing the value of s for each of those values. Since print automatically adds a new line at the end, the upshot is I will display hello with each character on its own line. H-E-L-L-O on separate lines. All right. Now, it's frequent that you would like to go through a succession of integer values, like from 1 to 10, or from 10 to 20, but only every other one. Or maybe you would like to count down from 10 down to 0. It's very common to want to count sequential integers, possibly with gaps, either in the up direction or the down direction. And An iterable that's built into Python that you can use for this purpose is a function called range. Okay, so if I say for x in range 5, what range 5 is going to produce for me each time I access it is the next value in the range of values 0, 1, 2, 3, 4. 5 itself is the end of the range. It's actually one beyond the values that range will produce for me. So if I say print x, I'm going to get on separate lines 0, 1, 2, 3, 4. If I give 2 arguments to the range function, then the second one is taken as the value 1 past the end of the sequence. The first one is taken as the beginning of the sequence. So whereas range 5 gives me values 0, 1, 2, 3, 4, if I say something like 4k in range 5, 10, then 5 is going to be the first value in the resulting sequence, and 10 is going to be one beyond the last value. So in other words, the results... Try again. All right. So in other words, the values I'm going to get here are 5, 6, 7, 8, 9. And let's confirm that. Notice that I typed my required colon so that I'm not going to get yelled at. There we go, 5, 6, 7, 8, 9. If I specify 3 arguments, then the first and second are the beginning value and one past the ending value. The third argument is the step size. So if I said something like this, for m, well, m is a list. Actually, m may no longer exist. Yeah, m doesn't exist. But I'll use something else anyway. For j in range 10, 22, let's say. So the first value would be 10. 20 is one beyond the last value. My step size is 2, so I'm going to get 10. And then 12. 12 is strictly less than 20, so it will be displayed. 14, 16, 18. Now, following the 18, the next value would be 20, but because 20 is equal to 20, which is one too far, that won't be displayed. All right, so 10, 12, 14, 16, 18 is what I claim I should get from this. 10, 12, 14, 16, 18. Okay, there we go. Here on slide 15, we have examples similar to the ones that I just showed. One interesting example that I want to illustrate here is the idea of using a negative step size to count downward rather than upward. If I say for I in range 4, comma, -1, comma, -1, all right, -1 is beyond the end of the range, but in this case, the range is going downward, and my step size is -1 rather than the default, which is +1. So the first value I'm going to get is 4, and then 3, 2, 1, 0. So 0 will be displayed. Now, following 0, when I subtract 1, I get -1, and because that's equal to the ending condition, that's not going to be displayed. All right, 4, 3, 2, 1, 0. Well, so that gets us through introducing the list collection type, which can be defined, a literal list can be defined using square brackets with values between the brackets separated with commas. We talked about how to create lists, how to index within them, either forward or backward, and also how to access and modify lists using symbolic operations like plus and times for concatenation and repetition, and also using named operations like append and insert and pop and sort and some others. We took a look at the sort of painful distinction, the annoying distinction in Python between a physical line, which is just whatever characters you type up to when you hit the enter key, that's the physical line, and then a logical line, which contains a statement of Python code. Very often, a physical line will be also a logical line. But sometimes a logical line, sometimes a Python statement, gets to be sufficiently long that it's impractical or ugly to type it on a single physical line. And so you may need to split it across multiple physical lines. You can do that either using the backslash at the end of the physical line, or more oftenly, people tend to use parentheses or square brackets, or later we'll see that you can use curly braces to extend a logical line across multiple physical lines. We saw that you can step through the items in a sequence, such as a list or a string, by using this thing called a for loop. And often in a for loop, the range function is used to specify a sequence of integer values. By default, counting up, but through using a negative step size, you can we'll try again. But by using a negative step size, you can also count downward in a range. Lists and strings are examples of what are called sequences in Python, because you can index them using 0, 1, 2, 3, and so on. Range is also a sequence, gives you back values 0, 1, 2, 3, etc. And all of these things, in turn, are examples of a more general category of thing called an iterable. An iterable is something that can be iterated through or looped through, and we use a for loop to step through all of the items in an iterable. All right, so that gets us to the conclusion of week 1.